Marhaba. Okay, in this session we want to talk about the cardinality of sets. Cardinality intuitively means the size of a set or the number of elements inside a set. Okay, we've seen before that if the set contains finitely many elements, say 10 elements, 20 elements, 1 million elements, 1 billion elements, then we can use this number, the natural number, say 20, to represent the size of the set. We say the set has 20 elements. But what will we do when the set contains infinitely many elements, like the set of natural numbers or the set of integers or rational numbers or real numbers? So in this session and successive sessions, we want to develop a tool, a technique, a concept which will help us to measure the size of infinite sets. And these ideas are due to the German mathematician of the last century called Georg Cantor. He's considered, so let me write his name here. So Georg Cantor, from say late 18th and 19th century. Okay, he's considered to be the father of set theory. And set theory is the study of sets, but in other words, it's the study of infinity. Okay. Now, the basic tool he used to measure the sizes of infinite sets is bijection functions. So we need to recall and we need to understand again what is a bijection function. So suppose f from A to B is a function. So A is the domain, B is the codomain, and this is a bijective function. Okay, let's unfold this definition. So we know it's a function and we know it's bijective. Let's really understand what does these two words mean. Okay, so first it is a function. So what is a function? We know that since it's a function, it's an assignment which assigns to every element in A one element and only one in B. So because we know it's a function, we know that every A in A has exactly one image in B. Okay, so this is the first piece of information we know. The second piece of information, we know it's a bijection, and bijection means it's injective and surjective. Okay, if we know these two pieces of information, then what does it mean it is surjective? It means that every element in the codomain has at least one pre-image, right? And what does it mean it is injective? That any element in B can't have two or more pre-images, because if you have two pre-images, this means we have two elements in A with the same image, and this is forbidden by injectivity. So these two together, injective and surjective, means every B in B has a unique pre-image in A, right? So since we know it's a function, we know number one, that every element in A has a unique or one image. And since we know it's a bijective, we know vice versa, that every element in B has a unique pre-image. So these pieces of information, that it's a bijective function, will give us the following picture. This is the domain, this is the codomain, and we have the function, and the function is bijective, means that every element has one image, and every element here has exactly one pre-image, and every element here has exactly one pre-image, and so on. You see? So this is the picture of a bijection. Okay, so let me say color these with red. Okay. You see that since we have a bijection between the green points and the red points, what can you tell about the number of the green points and the number of the red points? Okay, you see that they must be equal, because every element here is assigned one element here, and every element in B is assigned exactly one element in A. So they are like go in pairs, and this means that the number of elements in A is equal to the number of elements in B. So this motivates the following definition. Let me define it. So definition, we say that if we have two sets, so two sets A and B we say that they have the same cardinality or the same size, the same cardinality. Okay, so this is the definition. They have the same cardinality if and only if. When do we want to say two sets have the same size or same cardinality? If there exists at least one function from A to B which is a bijection. If and only if there is at least one. If we manage to find just one, there is a bijection F from A to B. Okay, this is the main idea of today, that two sets have the same cardinality means, this is a definition, we define this term that they have the same size, the same cardinality. It exactly means that we can find at least one bijection F from A to B. Okay, and what is the notation we have the we write the cardinality of A is equal to the cardinality of B. So they have the same cardinality if and only if there is a bijection. Okay, there is a bijection F from A to B. Okay, so this is a definition. I'll put it. It is the same as I said, but written in symbols. So this is a definition, and we say two sets. Okay, we don't know what does it mean. When A and B are finite sets, that's fine. That the cardinality of A is 5 and the cardinality of B is 5. So we say they have the same size. But this is a more general definition of saying that two sets have the same idea. The definition say that we will consider two sets to have the same size, the same cardinality. So the cardinality of A is equal to the cardinality of B if and only if there is a bijection F from A to B. So if you are asked to show that two sets have the same cardinality, this means you have to provide us with a function from A to B and show that this function is a bijection. Okay, now let's go to the next idea. Now we want to give a special name for those sets whose cardinality is equal to the cardinality of the natural numbers. So remember what is the set of natural numbers? This is this is the set containing 0, 1, 2, 3, 4, 5, and so on. This is an infinite set and it contains these numbers, whole numbers. Now let S be a set, any set, be any set. Okay, we say S is called countably infinite. Okay, we say S is countably infinite. So if the cardinality of S is equal to the cardinality of the natural numbers. So if the cardinality of the natural numbers is equal to the cardinality of S. Okay, so this is if and only if. This is a definition. Now what does it mean that the cardinality of N is equal to the cardinality of S? Look here, what does it mean for two sets to have the same cardinality? It means there's a bijection from the first to the second. So this means, so i.e. there is a bijection, so there is at least one. Okay, there is a bijection F whose domain is the natural numbers and codomain is the set S. Okay, notice, do you remember what do we call functions whose domain is the natural numbers? We call them sequences, right? This is an infinite sequence. And since this is a bijection, so let me show you the picture here. We don't know the element, what are the elements of S, but we know there's a bijection from n to s. So this is n and this is s. This is 0, 1, 2, 3, and so on. So 0 has some elements, say let's call it a0. 1 has some image, let's call it a1. A2 has some image, let's call it a2, and so on, right? So this means countably infinite sets are those sets which can be listed, whose elements can be listed. So we can think of, since we have this bijection, and say the image of k is the element ak, and since f is a bijection, this means every element in S, right, has some pre-image, has exactly some pre-image. This is because it's a bijection. Then all of the elements of S are in the range of f. Okay, this means that S can be written in this way: a0, a1, a2, a3, and so on. Okay, so this is the idea of countably infinite. A set is called countably infinite if its cardinality is equal to the cardinality of the natural numbers, which means there is a bijection from n to s, which means we can list the images, the elements of s, which are the images of the natural numbers. Remember, what is a0? This is the image of 0, and what's a1? It's the image of 1. What's a2? It's the image of 2. So the existence of a bijection from n to s allows us to list the elements of s in this way: the first element, the second element, the third element, and so on. Okay, so these are countably infinite sets. Now the second definition is, we call a set S is called countable if and only if S is either finite, okay, or countably infinite. Full stop. Okay, so countably infinite means we can list its elements in the same way we can list the elements of the natural numbers 0, 1, 2, 3, 4, 5, and so on. If you can list the elements of S one after the other and you can list all of them, then we call S, and they are infinitely many, then we call S countably infinite. Otherwise, and also if you can list, there are finitely many elements in S, then the set is finite, so we can, there's a finite amount of them. Then these two types of sets, the finite sets, the finite sets and the infinite sets, which you can list their elements, both of them are called countable. Okay, so this is this definition, the definition of countable sets. Now let me tell you what is the definition of uncountable. A set S is called uncountable if S is not countable. And remember, not countable, what does it mean that you are not countable? Remember De Morgan's law, the negation of P or Q, which means it is not finite. So remark, so this means that it means two things. One, not finite, and two, what is two? Not countably infinite. What does it mean to be not countably infinite? It means there is no bijection. There is no bijection whatsoever. There is no bijection f from the natural numbers to s. Okay, so this is the idea of an uncountable set. It means it is not finite, so it's an infinite set, but not only it is infinite to the point that you cannot find a bijection with n, which means you cannot list its elements. You cannot mention all the elements of S. Okay, so let me draw a picture here of what we saw so far. So suppose this is the world of all sets. Then we have a collection of those sets which are called the countable sets. Right? What is a countable set? Look from here. A set is countable either if it's finite or countably infinite. Okay, so here the countable sets are divided into two parts. The finite sets, for example, the set containing 1 and 2, and the countably infinite sets, which are sets which have a bijection with the natural numbers. So in particular, the natural numbers have a bijection with themselves. And now outside this circle, the countable sets, we have the uncountable sets. So a set, we still don't know if there is a countable set, but if there is one, then this set is not finite, so it's infinite, and we cannot list its elements. We cannot put it in bijection with the natural numbers. Okay, let me finish this session with two more points. So now let's look, what does it mean when we have just an injective function? So we've seen above, before, when we have a bijective function between set A, set B, this means that they have the same number of elements. What does it mean when we have a function f from A to B, and this function is, all what we know about it, it's that it is just an injective function. It means that we have A here, B here. What is an injective function? It's a function which does not assign to two different elements in the domain the same element in the codomain. So it should look like this. And maybe B has more elements which don't have pre-images. Okay, so this is the general picture of an injective function. And see here, no two elements in the domain have the same image. You see, what can you tell about the number of elements of A compared to the number of elements in B? Look, the elements here, all the elements here in A have a unique copy in B. No two copies are identified here, right? If the copy of this element, so they are the red ones. So here, see here, all the elements in A have distinct copies in B, and maybe we have more elements in B. So all what we can say that the number of elements in A, or B has at least the same number of elements in A. The same number, at least the same number of elements in A. Right? Look at the set B. It contains 3 elements, the red, which are the images of A, and maybe more. So in other words, we want to say that the cardinality of A is less than or equal to the cardinality of B. That B has at least the number of elements in A, or maybe more. Okay, so this motivates the following definition. we say let A and B be any sets, infinite or finite. Maybe they are infinite sets, but we say that the cardinality of A is less than or equal to the cardinality of B if and only if. So this is what we mean. When we say less than or equal, we mean there is at least one injective function from A to B. There is an injective function f from A to B. Okay, so whenever we write this thing about sets, that the cardinality of a first set is less than or equal to the cardinality of a second set, we mean we can find an injective function from the first to the second. Okay, and the second point, we want to say that the cardinality of A is strictly less than the cardinality of B. Again here, maybe you think of A and B containing 5 elements and 20 elements, but what if the sets are infinite? So it doesn't mean that we need to find a precise way to define what do we mean by the size of an infinite set is strictly less than the size of another set. And it means, if and only if, it means two things are true. One, that the cardinality of A is less than or equal to the cardinality of B, and two, it means that the cardinality of A is not equal to the cardinality of B. But again, what is point 1? Point 1 means from here that there is an injective function from A to B. And point 2 means, how did we define that two sets have the same cardinality? It means that there is at least one bijective function from A to B. So they are not equal means the negation of this statement, that there does not exist a bijective function from A to B. Okay, so let me write all of this. So the cardinality of A is strictly less than the cardinality of B means that there is at least one injective function f from A to B, and there is no bijective function, say G, from A to B. Okay, let me say this in words again. The cardinality of A is strictly less than the cardinality of B means we have at least one function, which is an injective function from A to B. And if you examine any function whatsoever from A to B, you will find out that this function is not bijective. It's impossible to find a bijective function from A to B. Okay, so if these two points hold, then we say that the cardinality of A is strictly less than the cardinality of B.